Hello and welcome to our lesson on inverse matrices and determinants. Basically what we're going to be doing is sort of combining the concept of matrices with two more, let's say, obscure ways to solve systems. Okay, just a little recap of all the ways we've looked at to solve a system. We said we could solve by graphing, and graphing would be finding the intersections of the equations in our system. Now that's only really going to apply if we're dealing with just an x and a y in our system, and we're going to see some later that don't contain those. Now we could graph larger systems or consistent systems containing more variables, but we'd have to guess at the remaining variables. But graphing was an option. We also saw substitution as an option. Substitution where instead of starting with two equations, two variables, you try to get down to one equation, one variable to solve by using substitution. We also looked at elimination. Elimination where you're trying to add your equations together to eliminate a variable. We also solved using matrices. Now matrices, the process of using matrices was really just elimination without the variables, but another process nonetheless. Today we're going to look at how finding the inverse of a matrix can be used to solve a system. So we're going to use inverse matrices to solve. And then we're also going to look at finding something called a determinant to solve a system. And determinants, although they aren't matrices, they look a lot like matrices, and they are used in connection with matrices. And so I'm going to lump these last two, again, more obscure ways to solve into one lesson. So these, again, you're not going to like these, I promise you, especially in comparison to the other methods. I would say these first three that we looked at are going to be the ones that you're going to tend to go with. But I'm trying to expose you to things that you are going to encounter later so that when you see them later, it's not like, where is this coming from? Okay? So I'm going to try to expose you to these methods. Hopefully you can wrap your brain a little bit around what's going on. But at the end of the day, this is really for exposure. So if you're struggling with these couple of concepts, don't sweat it, just to do your best. Okay? This is going to be something that's going to be heavily tested, so don't freak out. Okay, so let's look first at inverse matrices. Now, inverse matrices are connected to something we call the identity matrix. So for a square matrix, a square meaning it's got n rows and n columns, same number of rows and columns. So for a square n by n matrix, the identity, which we would call I sub n, contains a diagonal of 1s and then 0s for all other entries. So for instance, for a 2 by 2 matrix, we've got 2 rows, 2 columns. Okay, so a 2 by 2 square matrix. We have this diagonal of 1s and then 0s for our other entries. For a 3 by 3 matrix, that's 1, 2, 3 rows, 1, 2, 3 columns. Then we would have a diagonal of 1s and then 0s for all of our other entries. And again, a 3 by 3 means our identity, or I sub 3 is our identity, and then for a 2 by 2, I sub 2 is our identity. Okay? Now these could get larger, but we're really just going to focus on a 2 by 2 because this is really just for exposure. So the identity matrix can be used to find an inverse of a matrix, and it can also be used to verify that we have the correct inverse for a matrix. So two things. How do we find it? How do we verify it? So we can verify with a property that we know to be true. If A is a square n by n matrix, again a square, same number of rows and same number of columns, and it has an inverse, we would call that inverse A inverse. Okay, so if you have a matrix that's square and it has an inverse, then the product of that matrix and its inverse will always produce the identity. So if you were to multiply your square matrix and its inverse, you will always end up with the identity matrix. And we'll just call this I sub n, since this really applies to any size a square matrix. Okay? Furthermore, So that's how we would verify. So if I said, here's matrix A, here's its inverse, if you wanted to verify that the inverse was correct, you could find the product of those two matrices and you should end up with the identity. Okay? So furthermore, not only can we verify, but we can use the identity to find an inverse. If we were to start with one matrix that puts side by side the matrix and its identity, then we can use row operations to manipulate this concept. So you're going to start with some numbers here, and let me just make something up, okay? Let's say we had 3, 1, 5, and -1 here. If we put side by side any matrix that has an inverse, a square matrix that has an inverse, if we put the identity next to it, so we have a situation that looks like this, that's what I'm saying here, just in a general way, what we would do here is use the same row operations that we talked about in solving. So swapping rows, multiplying rows, or adding multiples of rows to change a row to make this side look like the identity. Then what's left over here after we use those row operations will actually be the inverse function. Okay, so I'm going to show you in just a second. Just try to go with me for a second here. If we start with A, and we put next to it its companion, the identity matrix, and then we use row operations to achieve the identity on the other side, on the left, then what remains on the right is going to be the inverse. So the row operations would get us to the identity on this side, and what would be left on the right is going to be the inverse. Okay, so to go from here to here, we're going to use row operations, and that's going to leave us the inverse. Okay, so how does this look? Let's see. Now I don't have two inverses here, so I'm not, or a matrix and its inverse. I'm not trying to verify. I'm going to try to actually find the inverse of this matrix. Now, again, this is not a system here. This is just a matrix. There's notice no vertical line, no constants in there. So not a system, just a matrix. So how do I find the inverse of this matrix? So what I'm going to do is write this matrix, this 3, 2, -4, 5, with a vertical line separating it from the identity. So for a 2 by 2, the identity would be 1, 0, 0, 1. And then I'm going to use row operations to make the numbers that I have on the right here look like the identity. So I'm going to try to get a 1, 0, 0, and 1 on this side. And just make sure that I apply the row operations all the way across. So what I would do first, to get a 1 in this spot is divide row 1 by 3, or multiply it by a 1/3. It's the same thing. So I'm going to do row 1 divided by 3. Okay, so that's going to take me to my next step here. If I take everything in row 1 and divide it by 3, 3 divided by 3 is going to be 1, which is what I wanted. -4 divided by 3 would be -4/3. And 1 divided by 3 would be 1/3, and 0 divided by 3 is still going to be 0. So I want to make sure I apply the operations all the way across. Okay. Now actually I'm a little scared I'm going to run out of room, so I'm going to scooch this up here. So row 1 divided by 3 takes me to this next stop. Now I just manipulated row 1 there, not row 2, so row 2 is not going to change. It's going to come over 2, 5, 0, and 1. So I've got the 1 in this first spot. Now I need a 0 where I have a 2. So this is where we're going to add a multiple of another row. So we're going to multiply -2 times row 1, and we're going to add that to row 2 to get a new row 2. So -2 times row 1, -2 times 1 would be -2. -2 times -4/3 is going to be +8/3. And then -2 times 1/3 is going to be -2/3. And -2 times 0 is going to be 0. I'm adding that to row 2, which was 2, 5, 0, and 1, in order to obtain a new row 2. And that gives me a 0, 8/3, and 5. Let me just not goof. 8/3 and 5 is going to give me, as a fraction, 23/3. 23 thirds. Negative 2 thirds and 0 is going to be negative 2 thirds, and then 0 and 1 is going to leave me with a 1. So that is my new row 2. So now I have here, I did not change row 1. 1, negative 4 thirds, 1 third, and 0 still intact. What I did was add a multiple of row 1 to row 2 in order to change row 2. So my new row 2 is 0, 23 thirds, negative 2 thirds, and 1. Okay, so we've got 2 more steps here, and it should make sense that it's going to take 4 steps. If we're trying to get a 1, a 0, 1, and 0, that's 4 numbers we've got to manipulate, so 4 steps this would take. Okay, and then maybe organizationally, I'm trying to figure out how do I fit all this in here. I'm going to go back to where I started with this. Over here. Don't you wish you could just scooch your stuff like that, right? Now this, I'm going to have to fix. How do I fix this? Because you can't read it now. Well, I can get rid of it. You saw me do it. So I'm just going to pretend you know what I did there to go to that next step. Okay, so now, again, I've got the 1, got the 0. I need a 1 where the 23 thirds is. So I'm going to do multiply row 2 by 3 over 23. So 3 over 23 times row 2 is going to get me a new row 2. And so again, row 1's not going to change. It's still going to be 1, negative 4 thirds, sorry, 1 third, and 0. And my new row 2 multiplied by 3 over 23, well, 0 times 3 over 23 is still 0. 23 over 3 times 3 over 23 gives me the 1 that I did there. 3 over 23 times negative 2 over 3 is going to make the 3's cancel. That's going to be negative 2 over 23. And then 3 over 23 times 1 is going to be 3 over 23. Okay? So we're almost there. I just need to get this last spot here to be a 0. So I'm going to multiply row 2 by a positive 4 thirds and add it to row 1. So remember, to get those zeros, we're adding multiples of rows. Undo. Get rid of the highlight. Nope, too far. Okay, so next step, last step, is to do negative 4 thirds times row 2 and add it to row 1 in order to change row 1. So if I multiply row 2 by a negative 4 thirds, I know this is nasty fraction work here. 0 times negative 4 thirds is going to be 0. 1 times negative 4 thirds is negative 4 thirds. And then I have negative 4 thirds times negative 2 over 23, which is going to be positive 8 over 3 times 23 would be 69. And then negative 4 thirds times 3 over 23 is going to be a negative 4 over 23. Okay, ugly, but negative 4 thirds times row 2 looks like that. And the goal was to add that to row 1 in order to change row 1. Oh, why did I use a negative? I don't need a negative. Sorry, guys. This needs to be positive because positive and negative will cancel. So this is going to be positive. This will be positive, and this guy will be negative. Okay, sorry. So I'm adding this to row 1, which again was 1, negative 4 thirds, 1 third, and 0, and that's going to give me my new row 1. So I get 1 here, and the 0, which is what I needed. Negative 8 over 69 is going to be added to a third, and that's going to get me 5 over 23. So 5 over 23. And then 4 23rds and 0 is still 4 23rds. And that is my new row 1. And so when I rewrite this, finally, I have my new row 1 is 1, 0. I have space here. 1, 0, and then 5 over 23 and 4 over 23. Okay, and row 2 I didn't change. I was only messing with row 1 here. So row 2 was still 0, 1, negative 2 23rds, and 3 23rds. Okay, and that is it. That is all the work. Okay, with the goal. Oh man, hold on. I'm sorry. The goal was to get the identity. Let me erase this now because it's getting in the way. The goal was to get the identity on the left. So that's what we did here. The left side here is the identity. So once we have used row operations to achieve the identity on the left, what we have remaining on the right is the inverse. So everything that's left on the right here is the inverse. So now we can say, given A equals 3, 2, negative 4, 5, we can say that A inverse is the matrix containing the 5 over 23 and 4 over 23 and negative 2 over 23 and 3 over 23. And there it is. Okay, it's ugly, but that is the inverse for that matrix. Now you can see if we were to use a 3 by, or start with a 3 by 3, finding the inverse is going to take more work because we'd have to 1, 2, 3, 4, 5, 6, 7, 9 different numbers we'd have to manipulate there, right? And that would have to be all the way across. So that's a lot of row operations to have to manage, but it's doable, okay? And it's a good practice of what we looked at in the previous topic. So we're able to find the inverse. Now, we use the identity and the row operations to find the inverse. If I wanted to verify that was the correct inverse, I could then take A, multiply it by its inverse, and if that was correct, then I would get back to the identity with that product. Now, we're not going to do that because there's no space, but that's how we could verify our work. Okay. Now, again, Desmos is not going to do this for you unless you're able to find that Desmos matrix calculator, but like I said last time I tried to access it, it was under construction. Now you can look. If you have a graphing calculator, your graphing calculators do this, but you have to be fluent with the calculator to be able to do it. Now if you want to know how to do it with your calculator, and you all have different calculators, I can't explain all that, but just go on YouTube and type in finding an inverse matrix using whatever calculator you have, and something should pop up on YouTube. People have put these videos out there on how to use the calculator to do these things, okay? So feel free to look for the calculator or use the calculator to know how to do this, but remember this is just supposed to be an introduction to this, so don't freak out about it is basically the thing this boils down to. This is for exposure, don't freak out, okay? Just do your best. Alright, so now that we are able to find an inverse, finding the inverse of a matrix just for the sake of finding an inverse, not really so useful. There are other uses for this, but one of them is to find the solution to a system. So the solution to a system we can find by multiplying. If we multiply the inverse of the coefficient matrix from a system with the constant matrix from that system, then we will find the solution to the system. Okay, so if we were to take this system and write it as an augmented matrix, remember that word, where we put the coefficients 1, 7, 2, and 8, and then separate the constants with a vertical line, the negative 13 and 8. Okay, what we know to be true is that if we find the inverse of the coefficient matrix, and we find that inverse and we multiply it by the constant matrix, that product is going to produce the solution to this system. Now obviously it would be a lot easier to just graph this system, okay, but I want to show you how this works anyway. So this piece right here, we're going to call this the coefficient matrix. And then this piece right here, we're going to call the constant matrix. Those are the coefficients of our system and the constants from our system. So what we need to do is find the inverse of the coefficient matrix. So we're going to find the inverse of that coefficient matrix. Okay, so let's find the inverse. This is what we just did, okay? It's going to be super fun. And that was sarcasm, not super fun. So we're going to find the inverse. I need to make sure I have enough space. So I'm going to try to write kind of small. So to find the inverse, we're going to buddy up our 1, 2, 7, 8 with the identity 1, 0, 1, 0, 1, 0, 0, 1. Okay? Now, luckily, we've already got a 1 here. Hallelujah. One less step. Okay? So the next thing we got to do is get, we need to get a 0 here. And so we're going to do multiple of row 1. We're going to do negative 2 times row 1, and we're going to add that to row 2 in order to change row 2. And I'm going to have to work vertically on this one. So negative 2 times row 1 added to row 2 in order to change row 2. I'm going to work vertically just so I don't run out of space. Okay? So what's that going to look like? Well, negative 2 times row 1 would be negative 2, negative 14, negative 2, and 0. I'm adding that to row 2 to change row 2. So that's going to give me my new row 2, which is 0, negative 6, negative 2, and 1. So now I can rewrite this. Row 1 didn't change. It was 1, 7, 1, 0. I have a new row 2 because I added a multiple of row 1 to it. And my new row 2 is 0, negative 6, negative 2, and 1. Alright, so I'm halfway there. 1's achieved, 0's achieved. Now I need a 1 here. So I'm going to divide by a negative 6. So I'm going to do row 2 divided by a negative 6 in order to change that row 2. So I'm not changing row 1. My row 1 is going to stay... sorry, I got to work on my spacing again. Can I squeeze this up a little higher? I guess I should have just made this more pages of notes, huh? Bear with me. All right, here we go. So again, I did not change row 1. It was still 1, 7, 1, and 0. The goal was to manipulate row 2 by dividing by negative 6. So 0 divided by negative 6 is still 0. Negative 6 divided by negative 6 was the 1 that I needed there. Negative 2 divided by negative 6 is going to be positive 2 over 6, which is a third. So 1/3 there. And then 1 divided by negative 6 is going to be a negative 1 over 6. Okay? Last step is to get a 1 here. So I'm going to do negative 7 times row 2 and add that to row 1 to change row 1. I'm going to add a multiple of row 2 to row 1 to get that 0. So negative 7 times row 2 is going to be 0, negative 7. Negative 7 times a third is going to be negative 7/3. Negative 7 times negative 1 over 6 is going to be positive 7 over 6. And I'm adding that to row 1, which is 1, 7, 1, and 0, in order to get my new row 1, which is 1, 0, negative 7/3 and 1. I can do that in my head, but I just sometimes don't trust my head. Okay, so I'm adding 1 to get me negative 4/3. And then 7 over 6 can stay. Okay, so now I'm done with this portion. My new row 1 is 1, 0, and negative 4/3, 7 over 6. Row 2 didn't change. It was still 0, 1, 1/3, and negative 1 over 6. Okay, so that's the first half of this process. We have to multiply, go back up here, multiply the inverse of the coefficient matrix, which is what we just found. This is the inverse of our coefficient matrix. We have to multiply that with our constant matrix. So the constant matrix is what we have over here. Now I gotta get rid of all these highlights. So the inverse matrix, actually the inverse, nope, I wanted my highlighter. Inverse matrix, that's what we have here. That has to be multiplied by our constant matrix. So now I'm going to take this constant matrix and I'm going to multiply. I was trying to make this look kind of uniform, but by the inverse. So how is that going to look? We're going to take the inverse, which was negative 4/3, 7 over 6. Well, let's see, 1/3, and then negative 1/6. That was our inverse. That is going to be multiplied by the coefficient matrix, or sorry, the constant matrix from our original system. So it's going to be multiplied by the negative 13 and the 8. And according to this property, which we know to be true, the messenger here, okay, according to this property, if we multiply that inverse and that constant matrix, we will obtain the solution to our system. So now we got to remember how to multiply matrices. So when we're multiplying matrices, remember, this is a 2 by 2 matrix, and this is a 2-row and 1-column matrix here, so 2 by 1 matrix. When we're multiplying, these dimensions have to match. They do. And so if these are equal, we can multiply, which makes sense because we're using a property that we know to be true. But the product, the answer, is going to be given by the remaining dimensions here. So our answer is going to be a 2 by 1 matrix. And that should make sense as well because our answer is going to contain an x and a y. Okay, that's going to contain the solution to our system. So a 2 by 1 matrix. So a 2 by 1 matrix is going to have 2 spots. And remember, this is row 1, column 1 of our answer, and this would be row 2, column 2 of our answer. So here, to find this spot, let me change that color. To find this spot, I want to multiply row 1 and column 1. Okay, row 1 times column 1. So that's negative 4/3 times negative 13 plus 7 over 6 times 8. All right, ugly. And then here, to get row 2, column 2, I want to use not column 2. See what I'm doing here, guys? Just trying to mess you up. Row 2, this is still column 1. There's only one column. All right, row 2, column 1. So row 2 and column 1 to get that product. So that is going to give me 1/3 times negative 13 and 1/6 times 8. Whew, moment of truth. Okay, so we're here. Now let's just put this in the calculator and see what we get with this work. So we have negative 4 over 3 times a negative, no, not there, times a negative 13, and we want to add 7 over 6 times, get out of the fraction, times 8, and alright, so that's what I ended up with here. Just make sure guys, I felt like the answer was going to work out nicely, and so maybe you were noticing I made a little goof here. Among other goofs, this was a negative, which I forgot to carry over. So that negative needs to be there, and that negative needs to be there, and there, and there. Okay, geez Louise. Let's put a negative in there. There we go. I was expecting a nicer answer. So this should be an 8, and now we're going to do the other part, row 2, column 1. 1 over 3 multiplied by negative 13, and then minus 1, I said minus, 1 over 6, fat fingers, multiplied by a negative 8, and that gives me a negative 3 in this spot. So according to all this, this system should have a solution at or of 8 and negative 3. And that would be really easy to confirm. This is clearly, guys, not an efficient way to solve this system. Again, this is stuff that we use more for larger systems. This is just supposed to be an introduction. The easiest way to solve this system, I think, would be to just graph it. So let's go ahead and confirm. That would be a real shame if we did all that work and got it wrong. But let's confirm. If we were to graph x plus 7y equal to negative 13, according to this work we've done here, or I've done and you've cried about probably, these two lines should cross at 8 and negative 3. So 2x plus 8y equals negative 8. Alright, so what do they cross? At 8 and negative 3? They do. Thank the Lord. Can you imagine if I did all that and I made more mistakes and didn't catch something? That would be a real bummer. Okay, you can imagine, right? Because I've probably done that before. So there it is. We can find an inverse matrix using the identity, and we can find the solution to a system using the inverse. Craziness. Okay, so like it or not, one of the topics you needed to see today. Now, the second obscure way we can use to solve a system is with determinants. You're going to like this better. I saved the better one, the easier one for last. Okay, here. So using a determinant, the determinant of a matrix, the determinant of a matrix is the difference of the cross products. Difference of the cross products. We have to cross multiply the numbers that are in our matrix, and, or sorry, yeah, technically it's a matrix. So we take the numbers that are in there, we cross multiply, and we subtract those products. So the difference of the cross products. So if A, B, C, and D are real numbers in a matrix, then we're going to cross multiply A and D, we're going to cross multiply B and C, and we're going to find the difference of those cross products, and whatever we end up with there is called our determinant. Okay, so our determinant is just the difference of the cross products. So that's an easy thing to calculate, so let's try that here. And if we were to cross multiply 3 and negative 2, so 3 times negative 2, let me start with this. The determinant is going to equal 3 times negative 2, and then we're going to cross multiply 1 and 6, and we want to find the difference of those cross products. So negative 2 and minus 6 here means our determinant is going to be negative 12. Simple. So much easier than what we were just doing, right? Okay. If you want to try this next one, again, our determinant is going to be the difference of our cross products. So 4 times 2 is going to be multiplied 5 and negative 1. Going to be multiplied, and we want to find the difference of those cross products. So this is going to be 8 minus a negative 1, so, or 5 times negative 1 is going to be negative 5, but minus a negative makes that plus. So this is a plus 5 here, and so we end up with 13. So that determinant is 13. Okay? So there's a mathematician, well, there was a mathematician named Gabriel Cramer that developed what we now call Cramer's rule, and he basically found a way to use determinants to solve systems. Again, this is another obscure way that we can use to solve a system. Now, this can be done with 2x2s, 3x3s, larger systems, but we're just looking at an introduction here. We're going to try to keep things relatively simple, so we're going to focus on 2x2s. And if you have a 2x2 system, 2x2, 2 equations, 2 variables, then you're going to have a linear system, and the coefficients of x and y are what we're going to use to calculate the determinant that we just saw a second ago. We're going to call that the overall determinant. Now, we can also call or calculate something called the determinant of the x values, determinant of x, or sub x, and that's going to use the coefficients of the y's, so the coefficients of the y's, and then it's going to use the constants. So it's still a determinant where we cross multiply and find the difference, but when we calculate the determinant of x, the d sub x, it's going to use the coefficients of y's and the constants. So what happens is the constants replace the coefficients of x, okay? And then we can also calculate a determinant of y, or d sub y. And d sub y, what happens is the constants replace the coefficients of y. So we still use the coefficients of x, but the constants replace the coefficients of y. So for the determinant, sorry, get rid of all this. For the determinant of x, we replace the coefficients of x, and for the determinant of y, we replace the coefficients of y, and we replace them with the constants from our matrix. Okay? So, if we can calculate each of those different determinants, as long as our overall determinant is not equal to 0, then our solution, remember it's going to have an x and a y value, will be the determinant of x divided by the overall determinant, and then the determinant of y divided by the overall determinant. It's a lot of determinants, but it's an easy thing to calculate. It's just make sure that you're organized with your work, okay? So here's how this works. First, we're going to find our overall determinant and make sure that it's not 0. So our overall determinant is just going to use all of our coefficients. So all of our coefficients. So according to the lettering up there, we would call this A, and then B, C, D, and this would be like our S and T, okay, if you want to try to follow the formulas. But I'm just going to show you the process here. So our overall determinant is going to be using the 3, -2, 6, and 1. It's just going to use, why am I still red here? It's just going to use the coefficients, not the constants. So again, 3, -2, 6, and 1. And we're going to cross multiply and subtract. So 3 times 1 minus -2 times 6. So 3 minus a -12, or 3 plus 12, is going to make 15 here. So this is 15. So our overall determinant, I have space, yes. Overall determinant is going to be 15. Okay, now we're going to find the determinant of x. So d sub x. Determinant of x is going to replace the coefficients of x from our overall determinant there. It's going to replace the coefficients of x with the constants. So in place of the 3 and 6, I'm going to put the 4 and the 13, but I'll still use the -2 and 1. So when I cross multiply here, it's 4 times 1 and -2 times 13, and then I want to subtract. Subtract the cross products. So that's going to be 4, this is going to be -26, and if I subtract a -26 I get a plus, so I end up with 30. So 30 for the determinant of x. Now I'm going to find the determinant of y. So when we find the determinant of y, we want to replace the coefficients of y with the constants. So now I'm going to replace the -2 and 1 with 4 and 13, but I'll keep the 3 and the 6. So I'm going to cross multiply 3 and 13 and 4 and 6, and then subtract. So that's 39 minus 24, which is going to be 15. Okay, so now we can get to our solution. According to Cramer's rule, our x value in our solution will be taking our determinant of x and dividing by our overall determinant. So the determinant of x was 30, and our overall determinant was 15, and so 30 divided by 15 means our x value in our solution was 2. And then our y value in our solution will be found by dividing the determinant of y by the overall determinant. So the determinant of y was 15, the overall was 15, and 15 divided by 15 is 1. So the solution here is going to be at 2, 1. So if we were to graph those two lines, they would be crossing at 2 and 1. Okay? That was not so bad, and I showed all the work there. This is actually something that I would probably do in my head, but and if you're good with holding stuff in your head, then you can try it that way too. But a lot easier than using the inverses for sure. All right, so let's try another one. Or if you want to pause the video, this might be a good opportunity for you to try on your own. So our overall determinant, it's just going to use the coefficients here. So 5, 2, -1, 3. We're going to multiply 5 and 3. We're going to multiply 2 and -1, and we're going to find the difference. So 15 and -2 subtracted minus a negative, that's going to make that a 17 there. So 17 there. And now we're going to find the determinant of x. So we're going to replace the coefficients of x with the constants, which are 13 and 12, and we'll keep the -1 and 3. And so 13 times 3 and 12 times -1, and we find the difference. So 39, and this is going to be plus 12, so 30, 40, 51. 51 there. And then our determinants for y, we're going to replace the coefficients of y with the constants, and we're going to keep the 5 and the 2. So 5 times 2, or 12, and 13 times 2, and then we subtract. So that's going to be 60 minus 26, which is going to be 34. All right, so now, according to Cramer's rule, our x value in our solution is, again, our determinant of x divided by our overall determinant. So we're looking at 51 divided by 17, which is 3. And then our y value in our solution will be our determinant of y divided by our overall determinant. So that's 34 divided by 17, which is 2. So the system has a solution at 3 and 2. If we were to graph these two lines, that is the point where they would cross. Now again, it's still probably easier to just graph the two lines to find that solution, but now you see there is another option. And later on, when you go to take a linear algebra class, and I don't know that you'll see a lot of matrix stuff in calculus, but if you ever take a linear algebra class, you're going to see a lot of this. You're going to be thankful to have been exposed to it in this class. Okay, so you should have enough to work on your assignment, which won't be hopefully overly challenging. And again, this isn't going to be heavily tested, so please don't stress out about these topics. Just do your best with what you can. We're almost there. Okay. If you do have questions and you want to reach out, then just send me an email and I'll do what I can. All right, guys, take care.